So we have the pleasure of having Dr. Andreas Athienitis with us. Dr. Athienitis made his his university studies in mechanical engineering, both at the undergraduate as well as the PhD level, and he's now a professor at Concordia University in the Department of Civil and Environmental Engineering. So Dr. Athienitis' research interests are mostly centered around solar energy as well as energy efficiency. And he's a Canada Research Chair, Tier 1. He's the head of the Solar Buildings Research Network, which is written right here. This is a research network which is both academic as well as including a number of companies in there. This is funded by the National Science and Engineering Research Council of Canada, known as NSERC. So I will let Dr. Athienitis tell us more about the design of advanced solar buildings aimed at a net zero annual energy consumption. Thank you very much.
Thank you for inviting me. So, quite an interesting topic and a bit complex. So I'll try to go into the different angles of this timely topic. Just one point I want to mention. The name of our department is Building Civil and Environmental Engineering. So usually people don't realize we have the building program, which is unique. In fact, we are the only university in Canada that has the building engineering program. So that's very special to our department. And I'm going to relate that program to my talk, especially at the end, because we focus on the design of the building as a system. So even though I'm a mechanical engineer, I'm in a building civil environmental department. So engineering is quite broad, and you have the ability to move between the disciplines because they overlap a lot. And building is actually an interesting mix of mechanical, civil, a little bit of architecture also. So we try to prepare our people to design the building as a system, both the structure and the energy aspect and the lighting and the acoustics. So that's now a similar rationale was for the establishment of the Solar Buildings Research Network, funded by our national research funding organization called NSERC. So the rationale for that was to perform research aimed at developing cost-effective and affordable homes and buildings with an average of zero annual energy consumption. That means they produce as much energy as they consume for heating, lighting, appliances, and so on. The big picture. In Canada, buildings consume about 53% of electricity. So that shows you how important buildings are, mainly for heating, but commercial buildings have a high lighting and cooling load also. So that's really interesting. Although we live in a cold climate, we have these high-rise, all-glass buildings that actually need quite a bit of cooling for almost half of the year, and sometimes even in January, believe it or not. So we have a long way to go before we can achieve net zero energy consumption on a widespread basis. Buildings are also responsible for about a third of greenhouse gas emissions. Actually, you could argue that in some cases that can be, depending on how you count things, it can be 40%. Now, most Canadians own single-family homes, something very important about our country. Of course, as you know, we are a rich country, so we have one of the highest levels of home ownership. So there is an important interest for us to develop cost-effective and energy-efficient homes that will keep this kind of situation going, where people can own their own single-family home, which is energy efficient and comfortable. In Quebec, we produce a lot of hydroelectricity. so there is less of a pressure to reduce greenhouse gas emissions. But of course, there are other problems associated with damming too many rivers and things like that. So the energy picture can be quite complex. Hydro relies more, Ontario relies more on fossil fuels and nuclear, but is now moving strongly in the direction of solar and wind. So it has introduced a very generous program to produce solar power. They will buy it at a very high price, much higher than what they sell, so as to encourage the adoption of solar technologies. When you come up with a new technology, most of the time it is expensive. For it to become cost-effective, you must go into mass production. To go into mass production, you need incentive measures. That's where the government comes in, and the schools and the education aspect to inform the public. This shows you some of the breakdown of the energy consumption of a typical conventional home, close to 40,000 kilowatt hours per year. Do you know what a kilowatt hour is? Let me see. How many know what a kilowatt hour is? How many don't know? How many know what is the difference between energy and power? How many don't know what is the difference between energy and power? Okay, that's fine. I'll explain in a very simple way. Power is instantaneous energy flow. It's the rate of energy flow. So if I say I have a 50-watt light bulb, it means there is 50 joules per second flowing through that energy bulb. Now, some of that energy becomes light. Most of it becomes heat. So if you integrate, those of you that have you done, no, you have not done integration yet, what am I saying? Have you done integration? Yeah. Yes? Some of you, okay. Now, if you plot a power curve and you find the area under the curve, that's kilowatt hours. So kilowatts, 1 kilowatt times 1 hour is 1 kilowatt hour. So kilowatt is the unit of power. If you multiply that by 1 hour, so if you have an energy flow of 1 kilowatt over a period of 1 hour, you get 1 kilowatt hour. That's the energy consumed. And you can, of course, express it in joules by multiplying instead by 3,600 seconds instead of 1 hour. So you see there the portion taken up by space cooling, lighting, appliances, water heating, space heating. There was a program called R2000 program by the government to encourage higher insulation levels in houses, adoption of better windows so as to reduce energy consumption. That was called the R2000 program. So that houses built to that standard, and there is a similar one in Quebec called Novoclimat. Anybody heard of Novoclimat? Novoclimat? Anybody heard of R2000? Okay, so it's good that I came here, so now you heard about it. I guess that's one reason why I came here. Okay, so you have these funny names, and then you have these so-called advanced houses. This was a demonstration program. When the government wants to show new technologies, they do so-called demonstration programs. So they will get very advanced industries and government research laboratories to build new houses with new technologies to demonstrate these technologies. So this was in the 90s. So they demonstrated that you could reduce this energy consumption almost to 1/3. We went to about 14,000 kilowatt hours per year. So does anybody know how much 1 kilowatt hour costs? How much do you pay Hydro-Quebec for 1 kilowatt hour? Sorry. Anybody knows? Yeah, a few cents, something like 7 cents. Let's say 10. If you say 10 times, if this was 40,000 and you pay 10 cents, how much would it cost a year? $4,000. So, I mean, it's a significant amount of money. I mean, it's about That's what you pay to go to. How much do you pay to go to Marianopolis? About that? So I mean, it's not an insignificant amount of money, and the cost of energy is rising. So what's our objective? Our objective is to bring this down to 0. You see, if you draw a curve there, you bring it down to 0. How do you bring it to 0? You bring it to 0 by doing the kind of things these guys here have done in the advanced house, but you also generate energy. So you have a negative. Instead of having just these positives, which are consumption, you have a negative, which is generation. So it becomes 0. So that's the whole idea about net zero energy buildings. Now, here is a fact. The annual solar energy incident on a roof of a typical house is a lot more than its total energy consumption. So the question is, how can we use a lot of that energy to generate electricity and heat so as to get to 0 average energy consumption? So that's one of the objectives of our research at Concordia and in this research network that I lead. The design of a low-energy solar home that attempts to exceed the energy performance of an advanced house will be described a little bit in my presentation. There is some statistics that I'm going to talk about. Now, just a little bit about our network. It's a big network. We have universities, 11 universities, government labs, utilities such as Hydro-Quebec, architects, engineers, manufacturers. So this is a unique Canadian initiative based at Concordia in our department. Our long-term goal is development of the optimized solar building as an advanced integrated. Integrated means really everything fits together nicely. You don't have things which are oversized, so it becomes cost-effective. It's a combination of high-tech and low-tech. Anybody hear this word? Passive solar, passive houses? Okay, so now you heard it. So you'll see some pictures, so it's more optimized. It's more clear. Solar optimization is a key aspect. So we want to use solar energy to generate electricity, daylight, and solar heat, all 3 forms of energy. You see some of our objectives there. We are studying new ways of using solar energy, such as in the John Molson building downtown at Concordia. There's a new system I'm going to describe later. This is a building at Queens. So photovoltaics are used as shading devices. Photovoltaic cells, everybody knows what photovoltaic cells are? Solar modules. So these things basically use the photovoltaic effect to convert incident solar radiation into electricity with an efficiency in the range of 10 to 20% most of the time. So the other 80% is lost. Yes? Is it lost by heat? It's lost mainly as heat. So we try to use that heat. You'll see some of the ways we try to use that heat. You can have windows nowadays which are semi-transparent photovoltaics. So they generate electricity while transmitting daylight, so you can see through them. So there are new interesting opportunities with technology that we didn't have before, and these are increasingly becoming cost-effective. One of the things we are doing, we are investigating innovative design concepts for such buildings, but at the same time, we are also developing computerized simulation and design tools that engineers and architects can use to design them. Integration is very important. I mentioned that we can, integration means using energy generating elements as integral elements of facades and roofs. So these solar panels are then become the outer layer of the roof or facade. So they are not an add-on. They are like roof tiles, let's say. So functional integration, architectural, aesthetic are very important in what we are doing. I refer to this example. Actually, this is my own house. I built a solar house a few years ago, so I'll talk about that. So here is the big picture of the Canadian situation. Then we want to aim for an advanced house that will generate a lot of energy or so that it results in zero average energy consumption. Most houses have forced air systems. That's another characteristic that we can use to our advantage. The so-called mass means surfaces that can store thermal energy. So for example, if you have concrete or a wall with bricks, this can store a lot of thermal energy. Natural ventilation and passive heating or cooling are important, but currently underutilized. I'll talk about some of the technologies that we have developed to utilize both electricity and heat. Here's an example of a house that was recently built based on our design. So it incorporates research performed by my research group at Concordia. Here you see a photovoltaic system integrated into that roof surface. So it's the roof. It's hard to distinguish from the other metal roof, which is not used to generate electricity. So that's what we mean by integration. So basically, the technology becomes very smoothly integrated into the design of the building. It becomes part of the building. And I'll talk about it a bit later. Triple glazed windows. I mean, these windows that you see here are very inefficient. They are very old. I mean, in most buildings of this kind, that's the kind of windows we have. So basically, I mean, if you were to put triple glazed windows, you reduce the heat loss through them to about, I would say 1/4 of what you have there now. So that shows you that how we can combine different technologies to arrive at this net zero energy consumption. So it's south. Actually, this is close to south facing. I think you get quite a bit of sun in this room, isn't it? Gets really hot. So this can be very useful, but you need to control the solar gains. How do you control it? By having automatic motorized blinds that shut off or reflect the heat out when you don't want it and let it in when you want it. So we're talking about smart buildings that use a combination of technologies to basically come close to zero energy consumption. So you reduce the actual consumption and you generate electricity and heat, and that's how you do it. So geothermal heat pumps are another, yes?
Sorry, for the windows.
Yes?
Is there advantage over normal windows?
Yes.
No,
you reduce your heat loss a lot.
Reduce heat loss.
Yes.
Normal windows are
They are double now. I mean, I don't know, are they single? No, I would be surprised if they're single. Are they? No, I don't think they're single, they're double. I don't think there are any more single place windows anywhere anymore. So, okay, but there are special coatings also used to reduce infrared radiation heat loss. So there are special coatings that you don't see, which make a big difference.
Can you change your existing windows, which I just bought, to move to this system, or you have to buy a window?
You mean to change the existing windows? No, you have to replace them.
Yeah.
Yeah.
I was going to glaze them.
I mean, if they're fixed, you can always add another layer of glass outside or something.
Oh.
Okay, but that's if you don't open them. And it's definitely not advisable because you may get other problems. So you see some of the work that we did in collaboration with this company, Maison Alouette, who built prefabricated houses in the eastern townships. This was for the first time this kind of system was developed. Basically, a whole roof that is built like a solar electric and solar thermal collector, all as one system in the factory. So this is, these two guys are graduate students who are doing their masters and PhDs with us in building engineering, and they worked on the design of the system. And you see there are intakes, so air goes under the soffits and goes through there. So we get a lot of the heat that would otherwise be lost. So in addition to electricity, we generate heat. We heat the fresh air for the building. We can use that heat to heat water. So we use the whole roof as one solar collector, basically, that generates both electricity and heat. So this goes built in the factory and delivered to the site. These are the solar panels basically attached with epoxy that comes with them. And they're also screwed at the top. You see, these are air ducts that take the heated air. There is spray insulation on them. You see the assembly of the modules of this house. So this was done in a few hours. This is in Eastman, Quebec. So prefabrication can reduce the cost of solar technologies through integration.
Sorry.
Yes?
Like the house we've just seen, is that something that has been done by the research group, or
Yes.
is the house? Okay. So it's
Yes, it's a so-called demonstration project again. It's a collaboration between the research group and the industry.
Okay.
We do the design, they build it, and we monitor its performance also.
Okay, but there's no individuals who have houses of that kind?
No, actually the house has been sold now, and there's somebody living in it.
Okay.
Okay, just recently. Now you see the energy balance. How many of you have taken physics? I guess the first law of thermodynamics, and then this will be some optics also. Okay, so if you do a so-called, if you apply the first law of thermodynamics, if you have 1,000 watts of solar radiation, you have some reflection from there, let's say about 100 watts. Maybe you will generate 100 to 200 watts of electricity per square meter, I'm talking now. And then the rest of it would become lost as heat. By passing air from outside under that layer, we get some of that heat also, maybe half of it. So we generate both electricity and heat. That's why it's called photovoltaic thermal system. BIPV stands for Building Integrated Photovoltaics. The integration is with the roof, wall, or fenestration. Fenestration windows can be semi-transparent or can be shading devices. HVAC stands for heating, ventilation, and air conditioning system. Heat recovery may be open loop with outdoor air or closed loop. Now this is a bit complicated, so I'll just show it to you very quickly. The house has passive heating, this built-in integrated photovoltaic thermal system that can be used to generate electricity and heat. Now, some of that heat comes and goes through a hollow core slab, a concrete slab, so it hits the concrete slab, and some of that energy is stored because you get a lot of energy when you don't need it. So you have to store it for later use. This is some of the modeling we are doing. We predict the temperature rise of the air as it flows under the roof. You see some of the construction of this floor in the basement with concrete. There are channels through which air from the roof is passing to store the heat. This is the insulation under the concrete slab. Here you see some of the research that was done to do that. Another house will be even more ambitious than that one. This is the Alstonvale house in Hudson. It hasn't been finished yet, so I'm not going to show pictures from this one. You see the schematic, the basic idea. This house has a bigger, quite a large photovoltaic system, and it will produce enough energy, not only for its own needs, but also to charge an electric car for local transportation. So this is quite an ambitious project, and we hope that it's going to work as well as the previous one. So you see some of the energy flows, 7.3 kilowatts, 5.8 for domestic needs, 1.5 kilowatts for the car. There is also a greenhouse to grow some local food. So a real green project. It will produce 20 kilowatts of heat also. We'll have emergency power for sustainable transportation, sustainable food production. You see some of the concepts. So there is air that goes under the solar panels, gets heated, and we generate a lot of heat, useful heat, used with a heat pump. A heat pump is basically the kind of device you have in your refrigerator. So it's not a very complex device. What is complex is how to link these things together. You see some of the concepts. This is a picture from the house as it's getting built. Design of a single-family detached house. The two-story option is usually the best because it permits higher slopes that are needed to shed snow in winter. We don't have to have a boxy design. A solar house can look nice. So very often people think, okay, I'm going to stick these ugly things on my roof. Why? So you don't have to do that. You have to optimize the design of the roof and the orientation. You can have different shapes, of course. It has to be wider in the near south direction. It doesn't have to be exact south facing, between southeast and southwest. This shows you the solar radiation incident, solar energy incident on the roof per square meter on a clear day in March. You almost get even more than 6 kilowatts per square meter. So this is quite a lot of energy. So if you have a roof which is 50 square meters, you have 300 kilowatts. So that's a lot more energy than what you need on an average day in the house. So I'm coming to the design of my own house. It has this photovoltaic thermal system. As you see, there is no snow that stays on the roof. This is a parallel roof there. So integration really works.
So there's no snow on your roof because of the angle and because of the heat?
Yes. Yeah, and because of there is a cavity under it. Actually, my house was one of the finalists for the Domus Award from the Builders Association in Quebec. So one of the things you are going to know there, apart from the pool, is a lot of south-facing window area. That makes a big difference. And I didn't put triple glaze because they were a bit expensive at that time, but I still put double glazed with a low emissivity coating and an argon fill in the cavity. Those are still pretty good.
Is that the ones that they label Energy Star?
Yes, yes. I mean, they have to have good framing and those kind of things. And a lot of practical details like interior brick, which stores a lot of heat, plus and some concrete on the floor with a radiant heating system. So this is the main innovation there in the house, this roof with the solar panels, and that produce both electricity and heat. Yes?
I'm wondering about the geothermal power.
Yes?
Where does the heat come from for the geothermal?
From deep down the earth, around 400 feet, there is a loop of liquid methanol that goes down through a 400 feet double pipe, and basically it goes down, and by going down, it takes a lot of heat from the earth and then dumps it into the house. That's why it's called a heat pump. It's like your refrigerator. It has a heat pump. It takes heat from inside the fridge and dumps it at the back. At the back of the fridge, there is a coil. If you touch it, it's hot. That's because it takes heat from inside the fridge and dumps it into the room. But that's a very small amount, so you can't heat your room or with your refrigerator because it's a very small heat pump, but still a heat pump. But this is a big heat pump. You have a big loop, 400 feet deep, takes heat from down deep in there. There is so much soil there, you know, you can't freeze it. I mean, if you operate this continuously, you could potentially freeze it. But it's very hard to do that because you go quite deep. And the temperature deep down there, it doesn't change very much. It's about 6 to 9 degrees throughout the year. Our soil here, the top of the soil, it's usually the top 5 feet that freeze. And not even the top 5, maybe top 3 feet.
So you have central air circulating
Yes.
in your house.
Yes. One of the questions where you are designing these type of houses is the window type, of course, how much insulation to put. Here is some of the research we are doing. This is mathematical modeling. It's like an electric network, but this is a thermal network. You find where the heat is going. So this is a lot of what we do in our research, you know, basically quite a bit of math and physics, and of course applied to engineering. So these are the kind of things that you would do in our program in building engineering. A lot of the results of the simulations. Do you know this program, MathCAD? Yeah? You do? You have it? No. Okay. There is another one called MATLAB. All these are very similar. You see the kind of results of the analysis. We try to calculate the temperature in the room as a function of the weather variables. So we can predict the indoor conditions using mathematical modeling. So math and physics, basically. Thermodynamics. This is outside temperature from -15 to -5 on a clear day in February. And this is the room temperature. And with a floor heating, this is the floor temperature. These are some temperatures from my house, different zones of the house. During a day like this, the house did not need any heating because it's very sunny when it's cold in our climate. With very efficient windows, basically, you don't need any heating during the daytime and even during the night. With a well-insulated house, with south-facing, energy-efficient windows. So that's a very typical situation there. You see some of the temperatures. Again, the picture with the snow. Now, this is a typical output from my photovoltaic system. So this is the time, and this is the AC and DC power produced. So it's about 2 kilowatts. The area under the curve is about 12 kilowatt hours. So if you integrate the area under the curve, you find the total energy produced. The instantaneous value at any point is the power, the kilowatts. Actually, watts in that graph. 2,000 watts is, of course, 2 kilowatts. And you produce DC power, and then through an inverter, you change it to AC power. That's a bit complex there, so maybe I'll talk to you at university. So 12 kilowatt hours on this day. We generated 12 kilowatt hours. This was March 21st in 2007. Now the final project that I'm going to talk about is the John Molson School of Business. You know this new building downtown? Yeah. Okay. So there is a new photovoltaic system on this building, close to 300 square meters. As you are walking down St. Catherine, you see it from the back. This is the back facade. So the back facade is the more interesting side of the building, you know. So anyway, that was a trick that we used to convince the university to do this innovative system. We said it's the back facade, you know. I mean, yeah. Even if somebody does a mistake, it's the back. But now it has become the front. So you know, so because it's the most interesting side. So we have this this innovative photovoltaic thermal system. It's the most unique in Canada, actually, of its kind, and actually the first of its kind in the world. So close to 300 square meters. And it generates electricity and heats fresh air for the building, about 1/3 of the fresh air for the building. So this is a new building that was just finished. So we have specially designed solar panels, special brackets. There is a perforated cladding there. The fresh air of the building flows behind these panels. It gets heated, and then it goes into the heating and ventilation system of the building. So essentially from one building surface with an area of about 300 square meters, we generate both solar electricity up to 25,000 watts and solar heat up to 75 kilowatts of ventilation, fresh air heating. And the system also forms the exterior wall layer of the building. So it is not an add-on, it is part of the building. It's like the windows. You see some of the concepts there. The sucking of the outside air gets heated, generation of electricity from DC becomes AC through an inverter. Some of the airflow paths. Again, a summary here. So this PV thermal system is then fully integrated, and the mechanical room of the building is directly behind it. So that means the fresh air, which is heated air, goes into the main ventilation system. If it needs any more heating, it's heated there, and then it goes to the rest of the building. So this is what we mean by integration. It's an optimal orientation. It faces in a good direction, close to south facing, so you get a lot of sun. In the winter, the sun is low, so you get a lot of sun on this facade, so it generates more heat and electricity at that time. At other times, the electricity is more important, but this is really about making this an integral part of the building design. You see some pictures there, the mechanical room directly behind it, the installation steps, the holes there for taking the heat. You see a close-up there of the basic concept, the PV panel layout. Now this is very technical, so I'm going to go through it quickly. If you go into electrical engineering or even our building engineering, you'll learn a lot more about this. You see some of the installation steps. It's an engineered system. We can reduce the cost by adopting some techniques of prefabrication again, build all of these things in the factory as wall sections and come and put them together by crane. So you see the picture from the, so this is the engineering building and this is the business building, business school, the John Molson School of Business. Now, my last slide. What are the challenges to achieve this? Integration of solar technologies with the architecture and with envelope. Optimization and integration again. Thermal storage, passive solar design. Integrated control to reduce peak loads, the peak demand for electricity, to reduce the need for building more power plants. So it's not just coming to zero energy consumption. We want to reduce the need to build more power plants. Education of architects and engineers. This is one major challenge. That's why we have developed our unique building engineering program at Concordia. And of course, it's going through an evolution now. It's changing as a result of our research. The first things that change are usually the graduate programs, the doctoral and the master's. And then that goes down to the undergraduate program. So this is what I will leave you with you to think about. I mean, there are a lot of things happening, new technologies, some exciting stuff coming out that can basically turn buildings into zero energy consumers, reducing greenhouse gas emissions potentially by 30 to 40%. If you produce enough energy for an electric car, then you go even further. So at this point, I'm going to stop and answer any questions if you have any. Yes?
About the passive solar design, why do we call it
Because you don't, the sun comes in, and you don't move it around with fans or pumps. It just moves around by natural means.
So it doesn't really move at all. It's
Oh, it don't move at all, it's stationary. Like in this room, sun coming in, heats up the room, that's passive. Yes?
I'm curious about costs. You said that the house that you built has been bought by an actual family living in there and
Yes.
so on. It seems to me that the costs for building that must be huge, actually.
You get an increase of the cost by anything in the range $20,000 to $50,000.
On a straw of a usual house.
Yeah. Yeah. Like if you put a very good swimming pool, it will cost about $20,000. Okay, so it's of that range of magnitude. Think of a swimming pool or a kitchen, a good kitchen. So that's the kind of magnitude you are talking about. But that cost is going to come down through this prefabrication, mass production, just like computers. You know, a computer that is now $400 used to cost about $10,000 20 years ago for the same computing power. But of course now you can go and buy for $300 to $400 a very powerful computer.
And the houses in Eastman, I did see it when I came out of Bolton, that they
Yes.
have an office.
Yes, you
And
went
they
there?
sell- Well, I didn't go, I was gassing and I saw that.
Yes.
And they sell, or they had a place that they were
They sold it,
sold.
yeah.
They sell houses.
Yes.
In the township.
Oh yeah, they built houses in
And
this.
do they bring them somewhere else than just in the township, or?
I think they can do it in other places too.
Yeah, because it's pretty,
Yeah.
very interesting.
May I ask a question? I'm a student at McGill University. I'm Master of Architecture. Yeah, I'm curious.
Oh, you are at McGill,
Yeah.
and you came just because from my talk.
Yeah.
Okay.
Yeah.
Okay.
Just very, very interesting. With
Yes, I came once at McGill a few years ago and talked. Yeah.
Oh, yeah. And I'm thinking about the John Molson building. It's not a really zero.
No, it's not zero.
It's not zero.
No, it's not. It's far from zero. I mean,
Yeah,
there is a long way to go in the design of other parts of the building to make it zero.
Okay, yeah. So as far as I know, that's the most weak point for the building to lose energy is from the window. Because
Yes.
the John Molson building has whole facade of
Yes, absolutely.
windows.
Yeah.
Yeah, that's what I read. And I want to say that I'm learning this technology in Swiss with university, ETH.
Yes, I know them. Yeah.
Yeah, Professor Keller told me that the low technique, the high technique, low energy consuming
Yes.
concerns 3 points. The first is the whole package isolation system.
Yes.
The second is the external sentry system.
Yes.
Yeah, and the end is the low E window.
Yes. Yes.
Something like that.
Yeah.
I'm very interested in this.
Yeah.
But, in this building, we don't have the, how does it say, the space conditioning like the heat pump. Not in the John Molson building, right?
No.
Because the office building is very hard to have this kind of things.
I mean, I would say both architects and engineers have a long way to go in terms of education in order to be able to do these things. So there is a big obstacle there. The engineering and the architectural disciplines have to change. Yeah. Yes?
Is there any buildings in Montreal, commercial building, that's zero?
No.
No?
No.
In the world?
In the world, yes, there are a few. Yes.
About what they mentioned about the whole buildings have like glass facade. on
Yes.
it. Actually, the glass is usually like glazed, so the sun doesn't come in to reduce heat.
Design of transparent parts of the building is quite complex because sometimes you want the sun, sometimes you don't. You want to control how much comes in. So, I mean, that's
Yeah,
quite
no,
complex.
If too much sun comes
Yes.
in, it's too hot. and
Yeah,
too
yeah,
little, it's
yeah,
not
yeah,
light enough,
yeah.
so-
We are doing research how to control that and optimize that,
So
yeah.
have you come up with like the optimum level of like?
Yes, we have come with optimum design methods to determine that optimum and also to control it. Yes?
What happens in summer when you don't want too much heat in the house?
We are doing some research with control of motorized reflective blinds and You can achieve a lot with that.
And those glazed windows, they still give you privacy in your house? You don't want to be in an aquarium where everybody could look at you?
Yes, there is a way to achieve privacy. I mean, of course, if it is in your backyard, it's hard for others to see you.
Yeah, no.
Yeah, but if it's in the front, you can use Venetian blinds, which bring the light in, but they reflect it towards the ceiling. Yes?
How good can you be at actually accumulating the heat and the energy that you don't need when it's produced in too high amounts?
That can be pretty good, but we are working to make it better. Actually, thermal energy storage is a very important part of what we are doing.
Because you mentioned at some point, I think there were some floors somewhere.
Yes, you can store it for a couple of days. I mean, you can store it for half a day easily in the structure of the building. You can store it for 2 days also without much difficulty. When it gets longer than that, it's hard to store it.
So no joint work with batteries or something like that to accumulate the energy?
No, it's more about the heat.
It's more about
For storage of electricity, I mean, you sell it back to the grid when you don't need it. Any further questions?
So, like Marianopolis with a very flat roof, we couldn't do solar panel?
No, you can do it. I mean, it would have to be add-on with their own support structure.
Because Westmount Sustainably were kind of going, oh, we have a big roof, and they were looking at us, power some
Yes,
electricity to Westmount.
yes. Yes, actually, yeah.
It's nice to dream.
Yeah. Okay,
Thank
Yeah.
you very much.
you're welcome. Okay.